Hey everyone, sorry I can't be with you today. Hope you're having a good day today. We are going to learn today about section 3.4. It's symmetries of graphs. We talked about it a little bit on Friday before we left for the weekend, but today we're going to get it into it just in a little bit more detail. So let's take a look and see what's going on. So we did this example on Friday, and I'm going to actually change colors here so that we can see this a little bit better. But what we did was we reflected this over the x-axis, the y-axis, and around the origin to be able to show what kind of symmetries we're going to be talking about. So let's take a look first at the symmetry with the x-axis. So we're going to do x-axis symmetry here, and let's see what happens when we do that over the x-axis. So this point right here is at -2, 4. We're going to reflect that over the x-axis, and it's going to go down to the point -2, -4, -4. So it looks like we go from the origin down to there. And then it looks like we go over to this point, which started at, let's see, probably 6 and 3. And we are now at the point -6, -3, which is right here. Connect those, and we now have a graph that is reflecting, has symmetry over the x-axis. So what we notice here is if we started with a point up here, -2, 4, it reflected over, and the y-coordinate is now opposite of what it was before. So if we started with a point up here, let's say this one right here, xy, it's now down here on the point. The x-coordinate hasn't changed, but the y is now the opposite. So we went from xy to now we have x comma -y. Okay, so that's the new point on the graph. Let's try it with the y-axis. So the y-axis is going to put that point that we had right here before, -2, 4, and it's going to put it over here to +2, 4. So we have +2, 4 now. So it's going to come up and connect right there, and then we're going to come all the way over here to the point 6, 3. So now we have a graph that's reflection symmetric over the y-axis. So this time, if we had a point that started as x comma y, like maybe this guy right here, x comma y, it now reflects over here to, what we did was we left the y alone this time, and the x has become opposite. So just like with the 2 changed from negative to positive here. Every time we have an x, even though it's starting negative, now we would have a negative of a negative, so it would actually become positive. So it's flipping it over the y-axis by changing the x-coordinate. So xy is where we started, and we have gone to changing our x-coordinate, and the y stayed the same. Cool. All right, so that was y-axis symmetry. Let's take a look at the origin. So origin symmetry, like we talked about on Friday, is going to take all of our points up here and rotate them around the graph down to the bottom here. So let's start with our point again right here at -2, 4. So that's going to come all the way around the origin down to this point right here at 2, -4. So we connect right there. And then our point out here that started at -6, 3 is going to come around and be at +6, -3. And we connect right there. So what we've done now this time is we've taken every point x comma y, we changed the x-coordinate, check out that, -2 went to +2, and we changed the y-coordinate, that 4 went to -4. So we're changing both the x and the y, so it's going to go to -x, -y. So this time xy went to -x, -y. Okay, that was origin symmetry. So these functions have names as well. And x-axis symmetry, this is one we talked about on Friday where we said it's not going to pass the vertical line test, right? It's going to have a couple things that aren't going to work out. So this one actually is not a function. Not a function at all. So that's one that we usually don't consider. But the next two have special names. If you have y-axis symmetry like this, we call this an even function. So this is an even function. And if we have origin symmetry like this, we call that an odd function. And today we're going to talk about how we can prove these things. So, to summarize this, if you have x-axis symmetry, you're not going to have a function, but if you started with the point xy on your graph, I'm going to change colors here, we're done with the red. So if you have the original point xy in your graph and you have x-axis symmetry, then you're going to actually leave the x alone, and the opposite of y is going to be on your graph as well. And I shouldn't use f of x notation there because it's actually not a function then. So on the graph as well. If you have y-axis symmetry, so if we go back a couple slides here, if you have y-axis symmetry, that's where we said xy is on the graph. That means negative xy also has to be on the graph. And this time we have a function. This time it's on f of x. And if we have origin symmetry, that's where we had to change the x because it flipped over the y-axis, and we had to change the y because it also flipped over the x-axis. So that meant that negative x, negative y is also going to be on f of x. Now, there's some patterns we notice here. This one, like we said, is not a function. So that one we aren't really going to think too much about. It's not a function. But these two, we had a name for this. This was an even function if we had that y-axis symmetry. And if we had that origin symmetry, we called that an odd function. And we're actually going to talk about how to prove these things today. But first, let's look at our parent functions and see which ones are even and which one are odd. So remember, even means that we have that y-axis symmetry. And odd means we have that origin symmetry. So let's take a look at these. This first one looks like, if we take a point up here, looks like it rotates around the graph to the same point on the other side. Looks like that's rotating around the origin. So we have origin symmetry there, which means that this is an odd function. Now notice if we plug in the x value here, it maps up to its y value right here. I'm going to call that f of x. So we plug in that x down here, it maps up to f of x. If we go the same distance on the other side, over here, to negative x, this time it maps down the same distance, but it's the opposite. So down here, we have negative f of x. So it's the opposite. It's the negative y value is what we were talking about before. With our parabola here, we see we have y-axis symmetry. That cuts the graph in half. So this time, if we plug in x, and we plug in the opposite of x, they go up to the same place. And that's our even function, because we have that y-axis symmetry. But we see if we plug in x and we plug in the opposite of x, they both go up to the same place, which kind of goes along with our summary here, because if you plug in negative x, it still gives you the regular y value. Over here, with our cubic function, we see we plug in positive x and negative x. They give us opposite values. So that's our odd function, has that origin symmetry. We're spinning it around. Our square root function, well, you don't have anything in the third quadrant, so it doesn't have origin symmetry. We also don't have y-axis symmetry, so this one's neither. This guy down here, this is our inverse function, 1 over x. If we plug in our positive x and our negative x, it actually looks like those go to opposite spots, and we do have that origin symmetry here, so this is an odd function. The volcano over here, we have y equals 1 over x squared. We plug in the positive x and the negative x. It actually looks like those go to the same spot. So this is an even function. Has that y-axis symmetry on the way to tell it's an even function. Absolute value, we reflect it over that y-axis. Looks like we have the same thing on both sides. This is also an even function. And then our exponential, well, if you rotate it around, it would be down here somewhere. Don't have that working out. And also, it looks like we don't have y-axis symmetry, so this is another neither. Like I said, today we're going to focus on being able to prove these actually with algebra, not just looking at a graph, but algebraically. Let's take a look here and see what we can figure out. So how do we prove it? How do we prove that a graph is even or odd based on just its equation? So we're going to be given some kind of a function, f of x. And as we saw before, when we plug in the negative x, we get some information, because either we get the original function back out, then we have that y-axis symmetry and it's even, or we're going to get the opposite of the y-coordinate, and that's when we have the origin symmetry and it's odd. So we have this f of x, and what I'm going to suggest that you do is you immediately write down what the negative of f of x is. And we're going to do some examples with this, so you'll see it in a second. And then what you do is you plug in negative x into the function. So you're going to do f of negative x. And you're going to get one of two things. Well, you could get one of three things. So either you're going to get f of x. So if you show that f of negative x is equal to f of x, that means it's even. Because f of x is just another way of saying the y-coordinate. So as we saw in our first few examples, if you plug the opposite of x in and you get the original function out, that means it's even. Because that means that every time you put in a positive x and a negative x, they go to the same place. So that's when you're going to have that y-axis symmetry, because it's going to split it on each side. If you plug in f of negative x and you get negative f of x, that would mean that it's odd, because what that's saying is you plug in positive x and negative x, they're going to go to different spots on the opposite sides of the axis. So you have a point up here and a point down here. That's where you have that origin symmetry. It's coming around the origin all the way 180 degrees. You have an odd function. Now the third thing that could happen is you could get neither of these. So this would be something like the square root function or the exponential function. So if you get neither of those two, that's where you're looking at a situation where you have neither odd nor even symmetry. Okay, let's take a look at some examples here. So in this case, we have a function x to the fourth minus 2x squared plus 1. We're trying to show if it's even, odd, or neither. So the first thing I want to encourage you to do is just immediately write out the opposite of the function, because that's going to be one of the things we're trying to get. So negative f of x just is gotten by putting a negative in front of the whole function. So we have negative x to the fourth minus 2x squared plus 1. Then we can distribute that negative, so that is negative x to the fourth plus 2x squared minus 1. So these are kind of our two goals. We're trying to get one of those. If we get one of those when we plug in negative x, that's going to prove whether it's even or odd, because that's exactly what we said in our last slide. If we get f of x, we're going to have an even function. We get negative f of x, we're going to have that odd function. So to do that, we're going to have to do right here is we're going to have to actually plug in negative x. So let's plug in f of negative x. Now, when I have that negative x in the function notation, that means every x in the function, here and here, is going to be replaced by a negative x. Oop, went too far. So let's give that a shot. So we're going to put negative x into our function. So we have negative x to the fourth minus 2 times negative x squared plus 1. So now I'm going to actually perform these exponents on the negative x's here. So negative x to the fourth. If I take a negative and I take it to the fourth power, it's going to end up being positive. So that's just x to the fourth. And then negative x squared, same thing. When you square something, it becomes positive. So I just have minus 2x squared and then plus 1. So I have x to the fourth minus 2x squared plus 1. And what this is right here is, hey, it's the original function. So I plugged in f of negative x, I got f of x. And this is exactly how I want you to show this. You plugged negative x into the function, you did the math, and then, hey, you said, well, that gave me back out my original function. So we've shown is f of negative x is equal to f of x. Therefore, our function is even. Because when you plug negative x into your function, you end up with the original function, and that means that it's even. So if we were to graph this, we would show that it has y-axis symmetry, and it actually is an even function. Not a bad idea to graph that on your calculator and take a look at it and see that the y-axis actually will split it down the middle. It's kind of cool. All right, let's try another one. So here we have a new function. F of x is x cubed minus 2x plus 1. So right away, let's write out the negative of the function. That's negative x cubed minus 2x plus 1. Let's distribute it in there. That gives us negative x cubed, plus 2x minus 1. So I just changed all my signs because I distributed the negative to all three there. And now we're going to plug in f of negative x, because that's going to tell us if we have an even, an odd, or neither of those two. We're either going to get f of x, we're going to get negative f of x, or neither. Let's see what happens. So everywhere I see an x again, I'm going to put in that negative x. So I have negative x cubed minus 2 times negative x plus 1. So when you cube a negative number, it stays negative. So that's still going to be negative x cubed. And then negative 2 times negative x is a positive 2x, because two negatives make a positive. And then that plus 1 is still hanging out at the end. So let's take a look. Is it the original function? Well, it doesn't look like it, because we have a negative in front of the x cubed now, and we have a positive 2x instead of a negative. And we have that plus 1, that's still there. Let's take a look at the negative f of x. So negative f of x would be negative x cubed, that's the same, plus 2x, that's the same. But negative f of x has a negative 1 at the end. We have a positive 1. So this is not the original function, and it's also not the opposite of the function. So if I were to graph this, I'm not sure what it would look like, but maybe it would be something like this. It might look something like this, I don't know. Maybe something like that or something. So notice it's definitely not symmetric by the y-axis, but also if we spun it around the origin, it wouldn't go back to itself. Like this bump would be over here somewhere, this bump would be over here somewhere, and we wouldn't get the same function. So this is actually one where it's neither. We have neither the positive nor the negative, so we have not even or odd, so it's neither. Let's do one more here. So this time, we have f of x, it's a fraction. It's 1 over x to the 5th minus x cubed. And right away, I'm going to write out the negative of f of x, which is negative 1 over x to the 5th minus x cubed. Now, we talked about this a little while ago. If you have a negative fraction, that negative can go to the top or to the bottom. So like if you have negative 3/4, you can put it right out front like that, like I did over here with this fraction. Or you could write negative 3 over 4, or you could write 3 over negative 4. Those are all the same fraction. So I'm going to do that with this guy as well. I could also write this as negative 1 upstairs over x to the 5th minus x cubed. Or I could write it as 1 over, and then put that negative on the bottom. So it would be x to the 5th minus x cubed. Oop, that's a negative sign. So that's a minus x cubed. And I could rewrite that, distributing the negative sign, as 1 over negative x to the 5th plus x cubed. So any one of these on the right here would be a negative f of x. So let's plug in negative x and see what happens. So I put negative x where I see those x's up there. So I have 1 over, I'm going to have negative x to the 5th, and then minus negative x cubed. So once again, when you take a negative to the 5th power and a negative to the 3rd power, it stays negative. So I have 1 over negative x to the 5th. And then here I have two negatives. That makes a positive x cubed. So let's see what we ended up with. That's definitely not our original function because we have a negative in front of our x to the 5th, and we have a positive x cubed now, so it's not f of x. But if we look at our opposite f of x's, one of our options down here has exactly that. It's negative x to the 5th plus x cubed. So what we showed is this is actually the opposite of the original function. So this is an odd function. If you were to graph this, you would have something that has origin symmetry. It would come around to the bottom of the function. Not a bad idea to graph this one on your calculator too, just to see how that happens, that we have origin symmetry there. Let's try some book examples. So this graph, 1 over x squared plus 1, we want to show that it's symmetric with respect to the y-axis. That's another way of saying that it's an even function. So to do that, we plug in negative x. It's going to be 1 over negative x squared plus 1. When we square something, that negative goes away. So that's just going to be 1 over x squared plus 1. Hey, that's our original function. So we've shown that that's equal to f of x. So it's an even function, which means it has y-axis symmetry. Pretty cool. All right, let's try one of the book examples here. So this time it says, determine whether the function f maps x to 4x minus 2x cubed is odd, even, or neither. So we want to take a look at plugging in f of negative x. And our options here are either it's going to be the function, or we should also check the opposite of the function. So that's just putting a negative out in front. So negative 4x minus 2x cubed. That negative goes to both spots. So that would be negative 4x plus 2x cubed. So we're trying to show if it gives us the original function or the opposite of the function. We'll see what happens. So I plug in negative x here. I have 4 times negative x minus 2 times negative x cubed. That negative x is going to be a negative 4x. I'll pull that negative to the front. And then negative x cubed, when I take a number and cube it, it preserves that negative. So I can pull it to the front, and that gives me positive 2x cubed. Okay, that's the opposite of our original function. So we've shown us that this is equal to the opposite of f of x, which means it's an odd function. If you were to graph that on your calculator, you'd have that origin symmetry again. Worth taking a look at. One more here. So in this one, we have the function 1 over quantity x plus 3 squared. minus 7. So the parent function for this guy is just 1 over x squared. And if the parent is 1 over x squared, that looks like this. It's the volcano. And what we've done here is we've moved it, looks like left 3, because it's the opposite of what you think, and then down 7, because that 7 came from the y equals, and it was the opposite originally. So what we've done now is we now have, we've moved it left 3 and down 7. There we go. So this is our new origin right there. So our graph's going to look something like this. And they ask first for the equations of the asymptote. So since it moved left 3, our vertical asymptote is now x equals negative 3. And our horizontal asymptote, our y moved down 7, so it's y equals negative 7. And they ask for any lines or points of symmetry. So we definitely don't have y-axis symmetry anymore because the y-axis is right here. We don't have origin symmetry because this graph around the origin would be somewhere up here. But what we do have is we have symmetry over this line right here. So it's kind of like y-axis symmetry, but our y-axis like moved. So we now have symmetry over the line x equals negative 3. So you could say it's x equals negative 3 symmetric. Because if you flipped it over the line x equals negative 3, you would have the same graph. So a little summary here. You have an even function. That's where you're going to have that y-axis symmetry. You plug in negative x, and it's going to give you the original function every time you do that. So like you plug in negative x into x squared, it's still just x squared. Odd function, we have that symmetry around the origin. And if you plug in negative x this time, it's going to give you the opposite. So here's positive x. Negative x is going to give you the opposite thing on the other side of the axis. So what I'd like you to work on now in maybe groups is worksheet 3.4. So that's the one in your packet that has 6 problems that are laid out in a table. And that one actually is after the homework worksheet I want you to do. But you might have time to do both of them in class today. Be sure to email me if you have any questions, just noah.fransky@edinaschools.org. You might even get a problem answered in the video tomorrow if you ask me a good question. So feel free to email me. I'll take a look at that and try to help you out with any questions you have. Also remember, if you have a quiz to make up, that those are available in Mr. Murphy's room today. If you go across the hall and one door to the right, I think that's room 321, he'll have those make-up quizzes available for you. So, I love you guys. That's why I'm here. And I just forgot that I have one more thing to show you. We talked about the pirate problem on Friday, and we had quite a spirited discussion about it. I wanted to go through the answer here. So if you still haven't figured it out and you want to pause the video and give it a shot yourself, you're welcome to do that. I'm going to give away the answer right now, so if you want to stick around, you can listen to it as well. So some people figured out if there are 2 pirates, they'll split the gold. So at 2, they'll definitely split. And some people said, well, so it must be 2 pirates. But my question is, how did they get down to 2 pirates? How did they get all those pirates killed to be able to get down to 2? Because 2 people can only kill 1 pirate, right? Because if there are 3, those 2 will vote to kill. But at 4 pirates, pirates number 1 and 2 are going to vote to kill pirate number 4, because they know if 4 and 3 die, they'll get more gold. But 3 and 4 are both thinking, well, that's a pretty raw deal for me, so 4 and 3 will vote to save number 4, 1 and 2 vote to kill, and they would also split the gold. So the 4 people, they know they're safe, number 1, 2, 3, and 4, so they're going to vote to kill, 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 all the way until it gets down to 4. But again, those 4 people, they can only kill 3 pirates. So they could kill at 7, at 6, at 5, but what about at 8? At 8 pirates, let's think about that. 1, 2, 3, and 4 are going to vote to kill, for sure. Because they know if they get down to 4, they'll be able to split the gold. But 5, 6, 7, and 8, what they're thinking is, well, if 8 dies, then those 4 people are going to kill 7, they're going to kill 6, they're going to kill 5, so they all want to vote to save pirate number 8. Now let's think, okay, how many pirates can 8 pirates kill? Well, they could kill 7, right? So they could kill up to pirate number 15, but they couldn't kill number 16. So 16 is the next spot they would split the gold. you see a pattern happening here? We have 2, 4, 8, 16. So 16 would split the gold, 32, 64, 128. These are all powers of 2. And then 256, 512. The next power of 2 is 1024, but we started with 1,000 pirates. So if we start with 1,000 pirates, pirates number 1 through 512 know that they're going to be safe if it gets down to that number. So they will vote to kill pirate 1000, 999, 998, all the way down to 513, and 512 pirates will end up splitting the gold. Kind of a cool problem. So, hope you enjoyed that. Now I can say, I love you guys, that's why I'm here. Have a great day, and we will have another video for you guys tomorrow. See you soon. Bye-bye.